Next, we're going to look at memory. First, we're going to look at memory types. So we have a definition of the different stages of memory that we have in the system. Then we're going to look at how the system protects that memory. That's layering and hiding techniques, which we've discussed in other domains. And then we're going to look at memory addressing. There are some definitions you'll need to know here in memory addressing. So first, let's get a definition of our memory types. We have different areas, different regions of the system that have memory requirements, and some of them are very high performance demands and others are lesser performance demands. The higher performance, of course, is more expensive, so we generally have less amount of these higher performance types of memory. That highest performance type of memory is referred to as the register or the buffer. Now remember, the registers and buffers live typically on the substrate that holds the CPU itself. Then the next level we have is cache memory. Cache memory, there typically are two types. There's level 1 and level 2 cache. Level 1 cache lives on the CPU substrate with the registers and the buffers. Level 2 cache is generally physically and electrically close to the CPU. Then we have RAM. That's random access memory. That's what everybody's aware of. This is volatile memory that loses what it has stored every time you power down the computer system. Next we have read-only memory, ROM. Read-only memory is a programmable memory chip that is not volatile. In other words, it retains its memory even when the power to the device goes away. And finally we have virtual memory. Now because memory of all types are expensive, we very often need to increase the amount of memory that we have in a system, but we don't necessarily have thousands of dollars to throw at this very expensive memory. So what we do is we actually simulate memory on the very slow and very inexpensive hard drive. Hard drives are approximately 1 million times slower than typical RAM. So putting this in perspective, when we roll to virtual memory, that's our page file or swap file, we are dramatically degrading the performance of the system. Very often, the answer to the performance question is add more RAM. So we've already looked at buffers and registers on the CPU. Next we're going to look at the cache types. Again, as I indicated, we have level 1 cache, which typically lives on the CPU itself, extremely close to the CPU electrically and physically, and very high performance. We're talking nanosecond technology. This is billionths of a second, maybe 2 to 3 billionths of a second to access the level 1 cache. Again, it's very expensive and typically very small amounts of memory. Then we have level 2 cache. As we see in the diagram, level 2 cache is located very close electrically and physically to the CPU, but is not actually part of the CPU. It's generally mounted on the motherboard very close to the CPU. Again, we're talking nanosecond technology, a few nanoseconds to access level 2 cache. Then we see read-only memory. Again, read-only memory is non-volatile. That's the important thing to remember. When we implement or when we store data into read-only memory, even if the power is turned off, that data is still there. It's left intact so that it's available the next time we power up. So our BIOS program that contains instructions on how to boot up the computer and instructions, drivers, if you will, for all the components on the motherboard, this lives in what's called read-only memory. Typically it's placed in something called an EEPROM, an erasable, programmable, read-only memory chip. And finally we'll take a look at virtual memory. Again, virtual memory is when I don't have sufficient amounts of RAM, so I simulate more RAM by creating a large page file or swap file on a hard drive somewhere. Remember, hard drives are very, very inexpensive compared to true physical RAM, but they also are very, very slow compared to true physical RAM. Now, this swapping process is controlled by one of the executive services of the operating system called the Memory Manager. Specifically, a subcomponent of the Memory Manager is called the Virtual Memory Manager, and that's the guy who keeps track of when I've run out of physical RAM and I need to make more. he then pages out or takes sections of content that is in RAM that hasn't been accessed for a while and pages it in 4K pages typically out to the very slow page file that lives on the hard drive. He then keeps track of what's out there so that when we do request that information back, when we're actually trying to process that content again, he has to then page that information back into physical RAM so that the CPU can access it and begin to process it. Again, it's the virtual memory manager that manages the swapping of these pages from physical memory out to the page file and then back. When I need to create more room in RAM, this is called a page out. When I'm looking for content that has been paged out to the page file, that's called a page fault. And the page fault triggers a page in. That's when I take content from the page file on the slow hard drive and page it back into physical RAM. So when you are looking at the performance of a system, sometimes your concern will be page out, page faults, or page ins. So again, to summarize, we have different types of memory, going from fastest to slowest, most expensive to least expensive, and generally smaller amounts to larger amounts. We have the registers or buffers that actually live on the CPU substrate. We also have level 1 cache that lives on the CPU substrate typically, and level 2 cache that lives very close electrically and physically to the CPU itself. Then we have main memory, which would be called RAM, and when we run out of RAM, we then will use an area, a page file on the hard drive that is notably slower, but we can create gigabytes of page file space. And here again is that summary. This also adds to it some additional components such as input devices. Some of the things that the memory manager is responsible for is the actual paging out. Now, again, we said that was a subset of this executive service called the virtual memory manager. He's the guy who's responsible for the relocation of paged content that was in RAM and now may be living on the hard drive. And he then, of course, is required to keep track of where it is and knows how to put it back when we need access to that information that has been paged out. The memory manager also works with the security kernel of the operating system to protect access to these components in memory. The security kernel's job is to see to it that only authorized access of the data and instructions is allowed. And it's his job to actually generate errors and block access when unauthorized access is attempted. Here we see a diagram showing us the memory manager actually living between the applications and true physical RAM. When an application is launched, the memory manager allocates an arbitrary or created, fabricated numbering system, addressing system for the application. So the memory manager tells the application, you have the region from 6 gigabytes of memory to 8 gigabytes of memory, for example. So the application thinks he has 2 gig of true RAM that he can play with. Now, the memory manager then will move the application's processes into physical RAM. And so the memory manager keeps track of the physical address and how it maps to the virtual address that was given to the application. This again is an example of layering and abstraction and data hiding. The application doesn't really know where to find its instruction and its data in true physical RAM. It only calls its locations by the virtual addressing scheme. So this is memory protection by virtual addressing. So the application doesn't really know where his content is in true physical RAM. Further, we see 2 different memory sticks in this diagram. This could also implement a form of physical segmentation or isolation. We could say that memory stick number 1, the guy at the top, is used only for top secret data, and memory stick number 2, the stick at the bottom, can be used for lesser than top secret information and processing. So we have seen now logical isolation and layering versus physical isolation and layering. Some other memory manager responsibilities include the sharing of information. There are times where one process needs access to information that another process is working on. So we have to have programmatic channels predefined so that there are permissions allowed so that process 2 can access data from process 1. Otherwise, the security kernel would disallow the access and would probably terminate the process that's making the unauthorized attempt. Again, we also had mentioned earlier that the memory manager's job is to provide this logical organization. In other words, setting up the virtual addressing scheme, keeping it mapped, and then also making links or connections to procedures in other areas of memory. And finally, we mentioned the physical segmentation that I described on the preceding slide. So some definitions related to memory addressing. First, we have base address. I believe in the example I described a few moments ago, I declared that application 1 would have an address space that starts at 6 gigabytes, and he could run all the way up to 8 gigabytes. 6 gigabytes would be his base address. Now there's another term here, it's not listed on the slide, called the limit address. The limit address is the offset or relative address from the base address. The limit address is the upper region of memory that an application is allowed to access. So we would say your base address is 2 gigabytes and your base address is 6 gigabytes. That's where you'll find your processes, and your limit address is 2 gigabytes. So that would tell the application he could run from 6 gigabytes to 8 gigabytes and could go no further. If he tried to touch anything in any other address space, the security kernel for the operating system would probably terminate that process. In other words, the application would be killed. It would no longer be functional. So we have a base address of 6 gigabytes, and if I needed a process that was stored at 100K above that 6 gigabytes, that would be the relative address. So it would be application 1 with a relative address of 100K. The relative address says, starting at your base address, move up. And that's where you'll find the instruction you're looking for. And finally, we have the absolute address. Now, the program or application itself doesn't ever know what its absolute address is. Remember, this is this logical segmentation that the memory manager implements between the program itself and true physical RAM. The program implements or executes its processes, loads them into RAM, but doesn't actually know truly physically where they're located on those memory chips. It just knows to tell the memory manager, I need an instruction from my base address plus 100K, go get me that. And then the memory manager looks at his map, identifies the absolute address or physical address where the information is that the program is asking for, and then provides access to that instruction or data set. So here we see an example of the base address and a limit address. The base address would be the 30004, and limit address is how much higher am I allowed to go from that base address. So this identifies the lower and upper bounds of the memory space that an application or program is allowed to utilize. We also need to recognize that from time to time, processes need to share access to data and instructions. We also mentioned this DLL, or the dynamically linked library. These libraries have shared routines, so periodically these programs or processes need to access the same instructions from these DLLs. So we must have predefined programmatic procedures so that a process is allowed to access a process in another area of memory that is not his. So again, these have to be predefined, complete with permissions, privilege. Otherwise, the security kernel for the operating system will terminate the offending process. And that's exactly what I was describing. Memory protection. Again, when we allocate a program the region from 6 gigabytes to 8 gigabytes in RAM, if some other application or process attempts to, in an unauthorized fashion, access anything in that region, the security kernel for the operating system will terminate the offending application. In the Microsoft operating system, the error message reads, an application has attempted to execute an illegal instruction and has been terminated. You've probably seen that error message. That is an application or process who tried to touch something in a region of RAM that he didn't have permission to. Next, we'll talk about a memory leak. Now, a memory leak is typically the result of poor programming. This is generally where a process has requested a region of memory, in other words, a stack. He said, I need a stack and it needs to be this large so that I can get all my instructions and all of my data into the stack. And then when the process has completed, when the CPU has actually performed the work, unfortunately the programmer doesn't give that stack memory back to the system. And he actually continues to collect more and more and more stacks that he never gives back. As a result, that application consumes an ever-increasing amount of RAM until the system becomes starved for memory. As a result, the performance of the system gets worse and worse, and it could actually cause the system to fail. When a bad guy finds this vulnerability, this poorly written code that's called a memory leak, the bad guy can now tickle that application into making that same request that doesn't give back the memory. He just triggers the process over and over and over again until he effectively kills the performance of the system. This is a denial of service or DOS attack.